This unit is all about energy, not the energy you think of like electricity, but like the energy needed to move and to work around. And, well, it's in just about everything. It is a little bit electricity, but that's not its only form. We'll take a look. So energy in the more broad aspect is the capacity of a physical system to perform work. It has the ability to cause change, and it's measured in joules. Joules is our unit here. There's a lot of different forms of energy. You can hear my voice. That means there's an electronic thing making a sound, the sound of my voice, and that's a sound energy that gets to your ear. It might be running on batteries, which might have some sort of acid-base breakdown that's causing a chemical energy, or you might be able to listen to this because you ate certain foods and your body breaks it down and gets the chemical energy from that. You can probably see something out of this video because the device is making a light energy come out that you're able to see, and all of that is usually powered with your circuitry by electrical energy. It might get warm after a little bit, which is a thermal energy, or hopefully you're in some sort of heater or next to a fire, which is also giving you a thermal heater during these more winter days. Nuclear energy might be one of the ways that your house is getting electricity. We use nuclear energy sometimes in order to create power in our power systems and everything. And then mechanical energy, think about that as just the workings of anything that's moving. Even yourself, when you move around, you have a certain mechanical energy. So when we think about these forms of energy, think about how you see these all the time, day to day. And it might not just be in one form. Like I said before, you can see several just from one thing. We start with a battery that has a chemical imbalance in it of an acid and a positive and negative side. And so it creates an electrical energy through a chemical energy. The sun, it uses all kinds of energy. First of all, it starts by moving particles together and doing a nuclear fusion, which creates a huge amount of thermal energy. That's why it's a giant burning ball in the sky. And then you get not only the heat from that, but you also get the light from that. So that's light energy. Think about even a lightning strike, right? You can see it. That's a light energy. You can hear it. That's a sound energy. It'll start a fire. So that's a heat energy that comes from it. But it is electrical in its overall state of the movement of electrons. So there's all kinds of different things. Light and just everything you can see has to have light. Every they call it a dark body, has to produce a certain amount of light. And then we use machines all the time with mechanical energy. There's just tons of things around you. You need to look around your room, look around wherever you are, and think about the amount of energy that is constantly just circling around you, right? It's moving everywhere. So not only do we have multiple types of energy, but it often doesn't leave anywhere. It just changes from one form to another. We call this the law of conservation of energy. Let me show you something real quick. So over all of the toys I have on my desk, this one by far tends to draw the most attention. People think it's a little clanky machine. Well, it's not. It's actually called a Newton's cradle, and it demonstrates this conservation of energy law. So it's the idea that this is a system, and in my system, if I put work or energy into the system, I have to get that same amount out. It should conserve it. So if I pick up one of these ball bearings and I pull it back, I'm putting energy into the system. I'm moving one ball bearing out. So that means it should keep moving that one ball bearing. And so when I let it go, we see that it knocks one ball bearing out. Okay? Now, that's not surprising to most people. Even when I decide that I'm going to take two, if I take two ball bearings back, I now should get two ball bearings out. And as you can see, I do. But there's only 5 of them total. So what happens if I decide to move more? If I decide to move 3 back? So if I move 3 ball bearings back, it says I should get 3 out. And I do. It has to have the amount of energy that you're putting in come out the other side. So even if I take it to where I move 4 of them all the way back, it's going to leave 1 remaining, and I'm going to get 4 moving at any given time, because that's the conservation of energy. The energy that I put in is the energy I get out. Now, someone always asks, well, what happens if you move 5? Well, that's called a swing. And yes, all 5 do move. So let's take a look at this conservation of energy in a more written term. The law of conservation of energy states that the total energy of an isolated system, so that's a big deal, and I'll talk about that in just a second, why it's an isolated system, will remain constant, meaning it's conserved. That's the conservation of energy. So the big premise is energy can't be created or destroyed. All right, so you're not making new and you're not destroying it. You're just changing the form of it from one to another. And that gives us these lovely energy chains. So think about firing a cannon, right? Or firing a rocket. You have a chemical energy that actually expels it from the cannon, turns into a mechanical energy of kinetic energy as it moves, but as it goes higher, it ends up another form of mechanical energy, potential energy, which then converts back to kinetic energy. And eventually it's going to hit and cause all kinds of heat and destructive energy there at the final end. So you don't lose any of it, right? And this would be considered one system. But we need to think for a second. So if energy is never created or destroyed, why does it seem like things stop or things wear down? Even the little Newton's cradle that I showed you before, it started to end up wobbling at the end of doing the 4, and it almost looked like it was just swinging again. Well, that's because we don't have very good systems. So remember, an isolated system. That Newton's cradle tries to isolate things, but a better understanding would be think about the entire world. In the entire world is our system, then you're going to get that energy changing into something else. You heard the ball bearings clanking, so that was a sound energy. You could see them. It might even create a spark if it was dark enough. Probably not with that, but it might with certain things. Think about banging rocks together. And then it has a wobble to it, so a vibration. So there's energy going in all of those different areas and not just back and forth between the ball bearings. Now, think about it this way. So you have big, strong muscles that uses a chemical energy from your food to lift a weight, right? Now you can carry it upstairs, and that creates a potential energy you're putting into that. You can drop it, and it would lose that potential because it's going closer to the earth, and it would gain kinetic. But when it hits the ground, you think, oh, that energy's gone, but it's not. So that energy turned into a number of different things like thermal energy, sound energy. There's even something called elastic energy. Notice that divot, the amount of earth that it's moved. It's pushed things back, things that want to snap back in their different ways. Think of rubber band in that sense. But all of this has created different amounts of energy in different areas, and it dissipates out to where you don't have it in such a concentrated form anymore. And that's why we tend to think of this as losing energy. It is losing out of this system, but not out of the system of the world. So it's the idea that it isn't created or destroyed. It's just changed around, but it's hard to keep it in a small system. In the system of the world, yes, we see energy all the time. Think about how the plants grow and then die and then get eaten by this or decompose in the soil, that nutrients and other things. This whole movement around is energy going from one form to the next.